Good morning, everybody. Welcome to this TMS seminar. Today the speaker will be Alessandro Fracassi. Alessandro is born in Avezzano and get his master degree in chemistry at the University of Rome Sapienza with a work concerning the synthesis and the characterization of cationic glucosylated surfactant and their use in the preparation of liposome formulation. After his master degree, he moved to ETH Zurich, where he recently completed his PhD under the supervision of Prof. Yamotoshi, working on the preparation of lipid nanoparticles to be used as MRI contrast agent for the detection of atherosclerotic plaque. Today, he will get his seminar and he will talk us about the emergence of life. Please, Alessandro, when you want, you can start.
Thanks, Luisa, for the kind introduction, and thanks to the organizer for inviting me for this talk. As Luisa mentioned, I did the PhD at ETH Zurich, and I'm currently waiting to start my postdoc at UCSD, where I'll be working on this field. The field of the emergence of life. So we think life usually as a special thing, but chemically speaking, can we really say that it is really special? So, as a chemist, we like to approach to it looking at the periodic table of the elements, and the question is, where do the elements come from? From astrobiology and astrophysics, we know that they come from space, and if we look out in space, and we try to make a ranking of the elements, we can see that the first is hydrogen, followed by helium, and then oxygen, carbon, and nitrogen. And if we try to make the same ranking for living beings, we have roughly the same. So the ranking that we would get, it matches the ranking of the universe, except for helium, which we know is not really chemically reactive. If we would design something as complex as life, we would base it on carbon, which has a really rich chemistry, and we can make more molecules out of carbon than all the other elements combined. So it's not really surprising, and life could not be so special. So the question is, can life emerge by just mixing up chemicals? The emergence of life was never really discussed until 1859, when Charles Darwin published his most famous book On the Origin of Species, in which he claims that living beings are not immutable, but instead they change over time and evolve from a common ancestor. This is really related to the emergence of life, because if we are sure that there is a common ancestor, and if we know, and we have evidences of that life is not fixed, as he said, as Charles Darwin says, changes over time, then this means that going back in time, also this common ancestor has to be formed in some way, starting from non-living matter. If we look at the age of the Earth, we know that Earth is 4.6 billion years old, and that the first form of life formed in after 1 billion years, or at least we have evidences only of that time, whereas we have evidences of the first form of pluricellular life again 1 billion years after, 2.5 billion years ago, whereas complex life as we know it now is quite young. So if we look at this time scale, we see how life evolved from 3.5 billion years ago to now, and there are theories and evidences of how this happened, but how the transition from non-living to living happened is still a black box. The first advice comes again from Darwin, that in a letter to his friend in 1871 wrote, It is often said that all the conditions for the first production of a living organism are now present, which could ever have been present. But if, and oh what a big if, we could conceive in some warm little pond with all sorts of ammonia and phosphoric salts, light, heat, electricity, etc., present, that a protein compound was chemically formed, ready to undergo still more complex changes, at the present day, such matter would be instantly devoured or absorbed, which would not have been the case before living creatures were formed. So what Darwin is trying to say to us, actually to his friend, not to us, in this letter, is that to really understand the emergence of life, we should think to Earth as it was before life emerged, so in prebiotic conditions. And another famous scientist, famous in the field, Alexander Oparin, in 1924 published his most famous book, The Origin of Life, in which he makes two very important claims. The first one is there is no fundamental difference between a living organism and non-living matter. So this is really a chemist perspective. And that the growth and the increased complexity of molecules brought new properties, and this is a really important concept. So he is actually introducing the concept of emergence. So what he's saying is that we have to look at life, not just at living things, not just at the structure level, but we have to look at the properties. So life is a property that emerges when we put some chemicals together. And is life an inevitable consequence of chemistry? So far, we had only theories until the Miller-Urey Experiment of 1953, when Stanley Miller, he was just a student at that time, convinced Harold Urey to try an experiment to verify Oparin hypothesis. So he wanted to reproduce prebiotic conditions, which consist in reductive atmosphere. So he created like a flask with vapor water, methane, ammonia, hydrogen, and simulated the prebiotic lightning by electrical sparks, and he could observe the formation of the first amino acids. Even though nowadays we are not sure about those conditions, we don't know if those conditions were the actual prebiotic conditions, this experiment still tells us that organic materials can form in prebiotic environment, and this was a huge breakthrough at that time. To be noticed is also the date, 1953. This is the same date that the structure of DNA was solved by Watson and Crick, and that's why actually genetics didn't have an impact on this experiment, and Miller was mainly looking for amino acids, the bricks of the main components of proteins. So following these experiments, other scientists try to find the prebiotic synthesis of other compounds that are of paramount importance for life, like nucleic acids and sugars. But also another question arises: should we only look on Earth for organic materials? So at that moment, everybody was trying just to form molecules in prebiotic conditions on Earth. But we live in a universe, and meteorites are coming to Earth, so they could bring some material to us as well. And when scientists tried to analyze meteorites, they could see that they can be source of organic material too. And not only that, because on these meteorites, they also found that 6 extraterrestrial amino acids presented enantiomeric excess, so giving also some input to solve the problem of homochirality. So at that time, the field of the emergence of life was almost stuck, kind of stuck, because there were some breakthrough, and we knew that we could make molecules out of prebiotic soup, but how these molecules assemble and form life, it's a total different story. And as I said before, in 1953, the structure of DNA was solved, which means the genetics start to have really an impact in the scientific community. And the competencies in knowing what's DNA and what's RNA really were higher and higher. And this brought to the RNA word hypothesis. So RNA, everybody knows, is a polymer that we find in all living things and interacts both with DNA, and is also responsible for the synthesis of proteins. So is again of paramount importance for all living beings. The main evidences of the fact that RNA could be the first molecules that cause the emergence of life is that it's able to catalyze reactions and self-replicate. So let me open a parenthesis about the self-replication. In the field of emergence of life, people are always looking for molecules that are able to self-replicate and catalyze their self-replication. And this is why, if we look at this calculation, in an heterocatalyzed reaction of a rate of 1 molecule per second, to produce 1 mole of that molecule, we would need an Avogadro number of seconds, that is 6.02 times 10 to the power of 23. But in a self-catalyzed reaction that proceeds at the same rate, so 1 molecule per second, we would need only 79 seconds. That's why self-replication is one of the holy grail in the field of the emergence of life. Another evidence of the RNA word hypothesis is that RNA is present in many cofactors. One above all acetyl coenzyme A, in which we can see that the real active part is the thioester bond at the end of the chain, whereas, and we don't know actually why there's a nucleotide on the other end, and it looks like it's a reminiscence of the past, when the part had actually an active role in the catalysis of some reactions. And last but not the least, RNA is the main components of ribosomes. So, which means that the synthesis, at least what we can see now from observing living beings, the synthesis of proteins depends on the presence of RNA. And if we have a closer look to ribosomes, we can see that the active sites of the ribosomes where proteins are synthesized are made of RNA, and the proteins that make ribosomes are just around. Once people collected all those evidences about the RNA word hypothesis, they of course started also questioning that, because it presents some major limitations. So the first major limitation is that the field went back to the original question. So, okay, I understand that RNA can be important for the emergence of life, but how RNA formed, and how, even if it formed, how the right RNA formed, because it's a polymer, so the right sequence has to be formed. And moreover, there's another problem, that is the problem of the concentration threshold. So if we assume that we have a self-replicating system, as we saw before, with a KD of 1 micromolar and a concentration of B of 1 picomolar, then the formation of the dimer allows the self-replication. So we would have only the 0.0002% of dimer. And even in those conditions, if we take 1 microliter of this 1 picomolar solution, there are still around 600,000 molecules, which means that to have effective self-replication, we need a lot of copies of the same RNA. So RNA has to form in many copies, and this is not really a plausible scenario. So people started to look at other possibilities, and other possibilities, the lipid world hypothesis. So the concept is the same. We're still looking at self-replicating objects, but we're not considering RNA anymore, but objects made of lipids. This is because lipids, especially phospholipids, can assemble to give structures that are very similar to cellular membranes. A phospholipid, for example, is an amphiphilic molecule made of a polar head and of hydrophobic tails, and when we put phospholipids in water, it forms liposomes, so the closed double layer. And those kind of structures are spontaneously formed because in this way phospholipids hide the hydrophobic tails from the water, exposing only the polar head. So the main evidence for the lipid world hypothesis is that there's no other life other than cellular life, at least that we know, and the formation of the lipid assemblies can also help solving the concentration threshold problem. So the person that you see down in the picture is David Deamer. He's professor at UCSC, University of California, Santa Cruz. He's one of the pioneers and main supporter of the lipid world hypothesis. And he's in Kamchatka there, and he's pouring prebiotic soup in a warm little pond. So he's following Charles Darwin's advice. And in the prebiotic soup, he has put some amino acids, some nucleosides, and lipids. And what he did is that he poured that and then observed the formation of lipid assemblies, which possibly contained also other substances, and then waited for hydration and dehydration processes. And then when he went back to the lab, he observed the formation of DNA from the polymerization of nucleotide. As I said, this could solve partially the concentration threshold problem, because we can imagine that during the dehydration process, the concentration of the particle incorporated, the concentration of the substances incorporated in the formation of the liposomes increases until overcoming this threshold. And there is also another important effect, that is the overcrowding effect. So it seems like when liposomes form in a media, there is an all-in, all-out effect. And it can happen that all the material is contained all together in one assembly, whereas the other are completely free, as you see in the cryotime pictures that you see here. This phenomena is not well understood yet. There are people studying it, and it seems connected to the speed with which the liposomes form. So if they form really fast, they don't have time to encapsulate the molecules that are dissolved in the media, whereas if they form quite slowly, so in the process of the formation, other molecules can bind to the membrane, and if there is a certain affinity, then an overcrowded membrane, closed membrane could form, as the one that you see here. So the RNA and the lipid world hypothesis, they are different, but they are not mutually exclusive. And a Japanese group, the Sugawara group, tried to combine them, describing a primitive model cell cycle. So in this cell cycle, at least a simulation of a cell cycle, there are 4 phases, and every phase is started by a stimulus. So there is an ingestion phase, a replication phase, then the maturity phase, and then the division. And they could really achieve several complete cycles. Okay. And I want also give an outlook on other possibilities that there are out there to understand the concept of the emergence of life, and those are given by the synthetic biochemistry. This is because all the ones that we have seen so far are bottom-up approach. So there are people making up molecules and putting them together to form something that can resemble life, and from which possibly life could emerge. And in this bottom-up approach, people always looked at systems, at life as it is now. So it was inspired by living systems. Here, the chemistry is totally different than the chemistry that you would find in a living system, but the concepts are all there. So, for example, we can see that there's a catalyst. So the chemistry is based on the copper catalyzed azide alkyne reaction, and the catalyst is able to catalyze the formation of itself and the formation of the phospholipids that will form the phospholipid membranes. And I would like to conclude saying that at the end of the journey, we do not know how life emerged, and that we know that the formation of organic materials in prebiotic conditions is possible, but we also know that it can come from the space. There's also actually a theory that says that life itself could come from the space, and that's called panspermia, but of course there are no evidences of it, even if people are really looking into that. But even if we don't know how life emerged, we know much more about how molecules interact with each other to form those assemblies, and how those assemblies can behave thanks to supramolecular chemistry, and the main breakthrough of genetics are really helpful in understanding how living system can possibly be formed and evolve. And in general, we know so much more in those 70 years about living things, and all this knowledge, even though it didn't bring us much closer to the understanding of the process of the emergence of life, it gave us different eyes to look out at the world. So we are dealing with a much more difficult problem than the one solved in the past, but the accumulating knowledge will be the key to go close to the understanding of this process. Thank you for the attention. If there are questions.
Thank you, Alessandro, for your presentation. It was very clear, very interesting. It's true that maybe we never think about how life occurred, the emergence of life. I mean, we investigate replication process, biochemical process, but it's not so common to think about this aspect that is very interesting. I have a curiosity, being working with liposomes. I have a curiosity. You told that when liposome formation is slow, is it possible to have this overcrowding effect? How is it possible to control liposome formation?
Well,
maybe in nature we can imagine that in the emergence of life, or in that period, liposome formation was slow and many molecules were included in liposomes. So
no. So first of all, that's just So that's not a well understood phenomena, and that's just a speculation that, so people that found that gave this interpretation. And you cannot really control the speed with which liposomes form, but the idea is that if, whereas they are forming, other molecules that are dissolved in the solution are going to bind the forming membrane, this could slow down the process. And if there is then also an affinity among those molecules, other molecules could come in. But this is just an interpretation. There are no evidences of this. This is just an explanation of the observation, trying to give it.
So liposome, in any case, liposome was this this first liposome, let's say, these aggregates could act as something like a microreactor. So increase the concentration of all these molecules. Then.
Yes. So, for example, we can imagine that at the beginning there were like both lipids and RNA molecules, but this would solve the concentration threshold problem, because if you have a certain number of molecules, this could be overcrowded in a liposome, and then...
That's clear. Okay. So, maybe this could be also... I don't know, I was thinking maybe also mice, maybe also other aggregates, I mean other formal aggregates formed by lipids. Now we know liposome, micelles, and so, because also micelles can, like, obviously now they are used as microreactors, but in controlled conditions, so I don't know.
We are
about lipid aggregates in general, let's say.
I totally. That's why my last slide was about the outlook and looking at different forms, a different chemistry that could give us insight about how life could emerge. So we are always biased when we look at living things, and that's why people mainly work with phospholipids that give that kind of aggregates. But actually, the bigger picture would be, let's look at the compartmentalization process. Okay. And the compartments doesn't have to be a liposome, can be whatever.
Okay, so thank you. So another question from Marco from the chat. Has someone hypothesized life forms based on other atoms instead of carbon? Is this even possible?
Well, if it's possible, nobody knows. Yes, the people made other hypotheses, but they were never confirmed because this has several problems. So first of all, I had to answer with another question, unfortunately. So, are we able to recognize other forms of life? We're not. Okay, yeah. Statistically speaking, we can say that basing life on carbon makes sense in terms of chemistry, because the number of molecules that you can obtain and the dynamicity and flexibility of the structure that you can get from those molecules is higher than from other elements. But of course, we cannot exclude that other forms of life could exist.
Okay, so. If there are other questions, I ask to the participant to the TMS, please write them on the chat. There. Don't be shy. Okay, so, not at the moment. Professor Marco made a comment. I have to go. Really, many thanks for your seminar. And Professor Teti has another question. What is the probability that life is present out in the solar system?
That's a very interesting question. So, what is the probability? It's difficult to calculate, but there's a certain probability because I mean the chemistry is huge, and the universe is even bigger than the possibility that chemistry has. So we really do not have a reason to exclude that the life could emerge also elsewhere in the universe, unless unless we Drake quotation, I don't know what's that. Anyway, unless we think that the emergence of life is really a contingent thing, which means that the formation of the conditions for the emergence are so peculiar, then that reduces the possibility. But we don't have also reasons to believe that. So for what we know, it could not be so difficult, actually.
Okay, thank you. There is a comment from Francesco Salamida. Drake equation, I don't know.
Okay.
Drake equation, I don't know what does it mean. Francesco, if you want to participate to explain this comment, because I don't know. I don't know this equation. I confess, I don't know this equation.
No, it's just a comment on the question of Professoressa Teti that said that speak about the probability of having life outside the solar planet. There is this famous equation Drake that is calculating in some way. There are many versions of it, calculating the probability to have life outside the solar system based on the number of solar systems that you have, galaxy, and so on. You can complicate as much you want. That was just a comment that came to my mind because of this question of Professor Teti. It was not a question.
So yes, thank you for this comment anyway. So any other question or comments or curiosity? I haven't read anything from the chat, so I thank again Alessandro for your seminar, and I invite you to the next week to the seminar that will concern dark matter. So thank you all, and see you next Thursday.
There's a still question, actually.
Sorry. Just in time. What about the discovery of other forms of life in other planets? Maybe we should reevaluate everything.
Well,
let's start again.
Not reevaluate, but evaluate everything, because we don't really have looked so far. I mean, we are not really able to go far from Earth, and people are for sure doing that. The problem are the tools that we have in our hands. So, for example, when I spoke about the RNA hypothesis, the RNA hypothesis developed because of the development of genetics. So, in 1953, DNA structure was solved, and then we had so much knowledge about genetics that people started looking at everything, including the emergence of life, and we could come to certain conclusions. We were able, so our eyes changed, and we were able to see some evidences that before we were not able to. Right now, exploring our planets, it's not a feasible thing, but for sure it's something valuable to do, and definitely worth it.
Okay, thank you. Any other question? Just okay, Ayuna. How do people look for evidence of life in other galaxies? I'd ask, what techniques do they use, and what do they look for?
That's also a really nice question. So there's also a theory like panspermia. So it could be that life was brought to us. So since we cannot really go out and look for life, what we can do, Luisa, I cannot see you anymore. What we can do is to analyze meteorites. So we can analyze what comes to Earth. And yeah, so far no life was found on anything that came on Earth, but organic molecules were found. Yeah, of course, that's not enough, even because life could be just destroyed when meteorites are entering the Earth atmosphere. But yeah, that's our possibility right now, perhaps in a couple of centuries we'll have major breakthrough.
Really. Other questions? No, maybe not this time. So, thank you again, Alessandro, for your seminar, and we will see next Thursday with the seminar about dark matter.
Thank you for inviting. Thank you for everybody. To everybody.
Bye.